Ladies and gentlemen, welcome everyone. I am Dr. Roland A. Drolet, PhD in Biomedical Engineering from the University of Toronto, 1971. I am the developer and inventor of the RUMART PEM system that has helped over 1 million people all over the world who were suffering from all kinds of health problems. Today I'm with my son, François Drolet, gold medalist, Olympic gold medalist in Nagano, Japan, in short track speed skating. And now I'm trying to speed some explanation about simple laws of nature, okay, in the MKS system of unit. So these are rather simple equations. Some of them have been seen by a lot of people who studied high school physics, for instance, but some of them I've never seen by these people. But they are simple equations. I'm going to give a few explanations to give you the impression that you took an engineering physics course summarized in 10 or 15 minutes. Okay? The essential, the equations that are too complex are not there. Okay? So here we start with Newton's gravitation law. Okay? The force is gravitational constant, which is really a constant in the MKS system. It has this value. Okay. This is the attraction force between two masses, M1 and M2, that are a function of the distance between these two masses as the inverse of the square of the distance, meaning that if the distance between two masses is doubled, the force will be 4 times smaller. Okay? That's the law that applies between planet and the sun, except for Mercury, as I mentioned a little bit, that you need general relativity to really explain the details. But generally, for all other planets, this Newton's law of gravitation is sufficient. Now, this is always attraction between two masses. But in electricity, we have what we call Coulomb's attraction-repulsion law. It's a similar type of law as the force is as the inverse of the square root of the inverse of the square of the distance. But it can be attraction or repulsion, depending on the sign of the charge. Charges of the same sign repulse and of the same time attract themselves. And I want to remind you what I told earlier, that let's say between an electron and a proton, like in an hydrogen atom, this force is about 10 to the power 32 stronger than that force. So at the atomic level, the electrical forces are so much dominant compared to gravitational forces that they can be completely neglected. But the centrifuge law, or centrifugal law, whatever you like, is the mass times the square speed, tangential speed, divided by the radius of the orbit. Okay? In speed skating, you know what I mean by that. And if you have too much speed in the corner and you don't have the friction force to keep you on the track, you just go to the bend.
The board.
To the board. That's to the bend. Okay, to the board. Okay, so because I mentioned that because in all atoms, like in a hydrogen atom as an example because it's the simplest one. You have only one electron, one proton. Like in iron, you can have 50 protons and neutrons and as many electrons to be neutral. But in the case of hydrogen atom, it's much simpler. This is what we call simplest model is the Bohr model, B-O-H-R, great physicist who understood.
B-O-H-R?
B-O-H-R,
Okay,
Bohr, okay? And so actually here we have, so I'm going to go from different laws because the idea there is to go through about, I think, 70 laws. Okay, so this is in 15 minutes. It's about 1 law per minute.
Okay.
So we are back in our time maybe. But velocity of light, this is a law
Light?
of light, yeah? And it's the same velocity as any electromagnetic wave in vacuum or light, because light is an electromagnetic wave. So the square root of, the square of the speed of light is 1 over the product of dielectric constant multiplied by magnetic permittivity. In other words, the speed of light, the speed of light is created by the nature of the vacuum, the electromagnetic nature of vacuum. In other words, the speed of light is not a property of the source, it's a property of the medium. Once energy is sent, it is a resonance between the electric and magnetic property of the vacuum that determines the speed of light. And that's how space, like in parallel plate capacitors, for instance, or capacitance theoretically, that has a radius r, for instance, of one plate, of the 2 plates, it creates what we call an electric capacitor that can contain a certain number of charge. And the value of the charge we can contain in such a capacitor, it's the dielectric constant multiplied by the surface of the capacitor divided by the distance between the 2 plates. Maybe we have this later on, but I'm going to go quickly now here. V is tangential speed here, mass, R orbit is the radius of the orbit. Tangential speed is what we call angular speed multiplied by radius. Okay, so these are the definition of angular speed. And the inductance of vacuum, capacitance and inductance of vacuum are determined by the characteristic, the electric and this, and the size of the space considered. Okay, but when given a certain size of capacitor, it determines a resonance between this size and the size of the inductance and the inductance of the vacuum around it. And when there are charge, moving charge, it's simply spontaneously send an electromagnetic wave. So from space, it creates time. That's interesting. Yeah. And so let's get to magnetic circuit now, because our minute is over. So here we have what we call the magnetomotive force, which is like a, let's say, an electrical potential of an electrical circuit. Suppose whatever, an electric motor you want to. So you have the magnetomotive force is defined by the product of the number of turns, let's say in a coil, okay, multiplied by the current. So this is like the voltage force is equal to a certain resistance, magnetic resistance, which we call reluctance, okay, to distinguish it from electrical resistance, multiplied by phi. the magnetic flux, which is equivalent to the electric circuit. Okay, so the voltage, if you want magnetic voltage, is equal to reluctance multiplied by magnetic flux. And there are other equations. What is a reluctance? It's similar to resistance in electrical circuit. It's given by the length of the magnetic circuit divided by its permittivity, magnetic, and the surface cross-section of the circuit. And the magnetic flux is the magnetic field multiplied by the space in which you have the magnetic field. So it is a magnetic field multiplied by a space gives a flux. Okay? So now the self-inductance, which is defined by this equation here, we say that the number of turns multiplied by the flux is equal to L, we define as the inductance multiplied by the current. You see here, it's number of turns by the current. But if we place number of turns by the flux, it is proportional to the current, but with a parameter we call inductance. But what is the value of this inductance physically? It's the magnetic permittivity, the cross-section of the circuit, let's say in a metal electromagnet, here is a cross-section of the circuit, okay? So that's the S perpendicular, number of turns squared, divided by the length of the circuit. So the inductance is like a resistance. The more the circuit, the longer the magnetic inductance, the lower is the inductance. But the fact is that the surface there will increase. If the surface or the number of turns increase, it's the ratio of all this that will determine what is the inductance. The inductance is being defined by the constant by which you multiply current to get N times magnetic flux. So I'm not going to go in more details there, except that if you play with this equation, you find that flux is Ni divided by R, okay? And you find that the IL that you define there is number of turns squared divided by the reluctance. We simply eliminated the flux there using the other equation. So there, I'm not going further into these, but this is just to give you an idea of this inductance concept is a factor of magnetic permittivity, number of turns, and when we have simply parallel plate capacitor and the air around it, we consider one turn of vacuum. We don't have to have 20, 30 turns because it's just only one turn. And there, when you calculate the resonance between this capacitor and the inductance of the electromagnetic vacuum, you end up that the vacuum resonates at any frequency, depending on the size of your parallel plate capacitor. So this is an interesting model because it helps you understand how electromagnetic wave can have all kinds of frequency. In other words, the vacuum, electromagnetic vacuum, is a resonator at all electromagnetic frequency. Suppose you have a mass attached to a spring to the ceiling, and if you pull on the mass and you let it go, it will oscillate at a certain frequency depending on the mass and the gravity. But the vacuum, electromagnetic vacuum, can do that at any frequency. So that is really almost miraculous. And so you can calculate the equation of the vibrating mass oscillating, like you would hold a mass and pull it when it's attached to a spring and it oscillates. You can, the equation giving the resonant frequency of this mass, supposing there is no air, it's just in gravity, you find the very same mathematical equation for the resonance of the electromagnetic vacuum. Then you see that the elasticity, for instance, of the vacuum can be almost anything depending on the frequency of the electromagnetic wave. So in other words, we have to open our mind when we study electromagnetism and all that, because it's not always evident with our sense. But the equation shows certain things and we measure it. So that's it. Eh?
Yeah.
Now let's go a little further. Electric circuit. Then it's what I was talking about, like magnetomotive force, reluctance times flux. Here it's a little more general than a voltage, an electric resistance like a stove resistor, and a current. It's what we call an impedance. An impedance can be a capacitive, inductive. It can have inductive, capacitive, and resistive. Okay. So this is a more complex thing. So here we come to the idea of complex number. So here the x-axis would be the resistance axis, okay? X. And the y-axis would be the impedance. And the negative axis, where axis, or x simply, would be the capacitance, because inductance retards the current in a circuit, but capacitance let the current through. The faster is the frequency, it can go like a short circuit. So the combination of an inductance and a capacitance, like in air, when it's in resonance, there is no electrical resistance. So the advance of the phase of the current and the retarding of the phase by the other component, okay? Retarding is from inductance and advance is from capacitance. It means that there is no resistance at all. So actually, this is why when charges are moving in a capacitor, it automatically sends electromagnetic wave in air as a function of the size there is there. Okay, so that's interesting, and these complex numbers help us understand, like an impedance there is a combination of real part, resistance, and what we call imaginary part. And this is the modulus of this vector, and the angle here is expressed by E, the base of Neperian logarithm, or natural logarithm, either to the power I theta. Theta is simply here, and I is square root of -1, just to make it sound interesting. But E to the power I theta is simply, this is simply cos theta plus G, which is square root of -1 sin theta, okay? Vectorially, you have this square plus this square, it gives this square. Okay, this is Pythagoras theorem. So this, you have been introduced to complex number realities, and now let's go quickly to the others. Now we see the simple laws of nature in rational and chaos system. This is a continuation. Now I'm not going to go into too much detail there, except it is a how you combine the various circuit elements in series or in parallel. In electrical resistance and in parallel, and in electric and magnetic circuit. So electrical resistance and inductance and reluctance, they add up in series.
Okay.
Okay? So if you have two the same value, it's twice. In series, equivalent resistance will be the sum, inductance, and so it's a summation of all of them that will determine. Whereas inverse of capacitance add up in series. For capacitance, it's the inverse of the capacitance that add up because they behave in much different way. In parallel, when you have two components in parallel, suppose you have two resistance of the same value in parallel, the equivalent resistance of the two will be half of the resistance because they are two places for the current to flow. Okay. So then in parallel, the resistance, inductance, and reluctance that were adding up, it's the inverse of this value that will add up. And in parallel, the capacitance which behave bizarrely here, they just add up. Because in parallel, the more you have capacitors, the more charge you can hold. Mm-hmm. So it adds up in parallel. Electrical and magnetic energies now in capacitors or capacitance. Capacitor is the physical thing, you know, that has parallel plates, okay? Yeah. Different size, whereas capacitance is the electrical concept defined by the equation, okay? And the same thing for inductor and inductance. So the energy in a capacitor is the charge multiplied by the voltage that we have seen over there, okay? So if you have an electron risen to 1 volt, it's 1 electron volt energy, okay? And in a capacitor, it's the capacitance multiplied by the square of the voltage because Q is CV, okay? So QV means CV squared because of this, okay? And similarly, the energy in an inductor is the inductance times the electrical current square. Electromagnetic energy per unit volume in vacuum. That's interesting. Energy per unit volume is the electrical energy plus the magnetic energy. But these are always equal, these two. They oscillate between each other. Okay. So this being equal to that, that means that the sum of the two is twice this. So it's this or this. Okay. But remember that one cannot exist before the without the other. Because it's the electric field circulating in a circuit that creates the magnetic field perpendicular to this. So one doesn't exist without the other. Okay. So as we have seen in Buddhist law, everything is interrelated. And we see it in physics, you know, and these are laws that are like ultimate. So just in a few minutes, I'm going to go quickly. I already mentioned Ohm's law. Volt is resistance times the current. This is like a stove resistance in ohms and current in amperes, okay? We talk DC, but in AC we can talk about RMS. Seeing the sine wave as efficient DC wave. So that's what we call RMS, root mean square. So the electrical energy in a resistance, spent in a resistance, is the resistance times the square of the current times the time, okay? In watt seconds. So you said a kilowatt hour, we pay the bill, it's roughly this, okay? Electrical power, power is times the voltage multiplied by the current, okay? And voltage is what is defined there, okay? Electrical power in watts is the voltage in volt times the current in amperes, okay? Simple fluid flow. The change of pressure determines, or P2 minus P1 at the end of a pipe, for instance, will determine the flow going through that pipe, okay, on water. Is the hydraulic resistance time to the flow, okay, well in hydraulic. But one thing interesting to remember when we talk about um, blood vessels in the body or any pipe, the hydraulic resistance of a pipe is inversely proportional to the fourth power of the diameter in a good range. So that means if you reduce the diameter by a factor of 2, like going out of your aorta, for instance, you have things stuck there, a diminution of the diameter by a factor of 2 will give an increase of hydraulic resistance by a factor of 16.
Okay.
So that's what causes heart stroke and all kinds of problems.
Yeah.
So this is very simple, but that you're never going to see pipes the same way.
Mm.
And we are full of pipes there in our body. Okay, so now L is the length of simple tube, for instance, the diameter of the tube, and hydraulic resistance. In units, it's kilogram per second, the flow that goes through, per meter square. Okay? Gravitational energy of a mass near the Earth, mgh, the mass times gravitational acceleration times the height. And if you let it fall, it will get, when it gets the ground, it will have the exact same kinetic energy as the potential energy that it had when you hold it still there. Okay? So potential energy going to kinetic energy. That's what happened with molecules and atoms in the air all the time. Potential kinetic, and they don't lose much energy because it's elastic bumping. Okay? So now the G, gravitation of the Earth around here, it's about 9.8 meter per square second square. H is the height in meter in this equation. Thermal energy. The change in thermal energy is the specific heat times the mass that you want to heat times the change in temperature in Kelvin degree. Okay? If it's a change in temperature, then it could be the same as centigrade, because it's just a change. So in this equation, you could change the centigrade for Kelvin, and it doesn't matter.
Okay.
Okay. Now we know that to raise 1 gram of or 1 cubic centimeter of water by 1 Kelvin or 1 centigrade degree, it takes 1 calorie, is the definition of calorie.
Okay.
But 1 calorie is 4.18 joule, the standard MKS unit of energy. So it's good to know. And the mass is in kilogram. So where H is in calorie, just what I said, CV, the specific heat in calorie per gram per Kelvin degree, or joule per kilogram per Kelvin degree when you use the right conversion. Note that as just what I told you before. And 1 centigrade degree is 1.8 multiplied by Fahrenheit temperature minus 32. Okay? Now, the last one but not the least, Schrödinger equation. Everybody talk about Schrödinger equation, but you never seen it probably. But you heard the term, because quantum mechanics, Schrödinger. So Schrödinger equation is here. You see, I showed you the complex number, because if I didn't introduce that, I could not even speak about that. Because I there is square root of -1. Okay? It's in a complex plane. H is the Planck's constant, and because there is a bar there, it's divided by 2 pi. Okay? It's a definition of this Planck constant with a bar. It's H divided by 2 pi. So the unit of complex number multiplied by the change, let's say that phi is the energy of an electron, okay, or a system. The change of energy of the system is reproduced with a question of angles, is reproduced by the multiplication of what we call an Hamiltonian times the same function. So this gives you the levels possible in the, I've shown you in the Bohr model the different orbits of an electron allowed around an atom. But this is much more general. But this equation can allow you to calculate the exact orbit of electron around the proton and even the elliptic orbit. So this is a wonderful equation, really, that I have learned in third year of physics, and Dr. Larkin Kerwin, who was director of the Department of Physics at Laval at that time, who later became the head of National Research Council in Ottawa, was my teacher of quantum mechanics, and he wrote a book to explain this equation so simply and so well done that the American, whole of USA, adopted his book to teach Introduction to Quantum Mechanics to high school students.
Oh.
So that's something. So Francois, I could go on and on for hours, but now this clip is over, and I'm glad that I explained it to someone who can absorb it.
Thank you,
Okay.
very interesting.
You have any question?
No, I guess it's the heart of your invention there,
Yeah, and it's the heart of science, really,
of science, yeah.
because 17 basic laws covering from gravitation, electricity, hydraulics, everything, really.
Everything's covered.
And talking about vessels in your body, understanding that how crucial it is when you have deposits in your arteries. And one of the basic things that Rumor does with the activation of circulation, it helps remove these deposits. So this is why some people, when people use Rumor regularly with these pulse electromagnetic waves similar to those of the nervous system, especially at the synaptic level, they could live maybe 20, 40 years older than they could have been without it. But it's not for most people to understand this, but I'm sure it's for you.
Thank you.
Okay, so have a good evening.